Welcome to Calculus 1. In this lecture, we will be calculating limits using the limit laws. Let's first begin with limits involving polynomials. A polynomial looks something like this, where you have p sub n of x is equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 all the way to a sub 1 times x to the 1 plus a sub 0. Note that here, a is just a constant number. Now suppose we want to take the limit of this polynomial as x approaches c. So it looks like this. The limit of p of x as x approaches c is equal to the limit of that whole expression as x approaches c. Now by the limit theorems we proved in the last video, we have the following. The limit of p of x as x approaches c is equal to a sub n times the limit of x to the n as x approaches c plus so on and so forth. Now we know that the limit of x to the n as x approaches c is equal to c to the n, and the limit of x as x approaches c is equal to c. So the limit of p of x as x approaches c is simply equal to p of c. In other words, you can find the limit of any polynomial by simply plugging in the limit point. Now let's talk about limits involving rational functions. There's a simple strategy for this. Cancel if you can. Other words, just directly substitute c into x. For example, let's evaluate the limit of 2x plus 1 divided by x minus 5 as x approaches 3. You can't cancel anything, so what we'll do is just directly substitute c into x. So the limit of 2x plus 1 divided by x minus 5 is equal to 2 times 3 plus 1 divided by 3 minus 5. So that of course simplifies to negative 7 over 2. Now let's try an example where we need to do something different. So we want to find the limit of x squared minus x minus 6 squared divided by x plus 2 as x approaches negative 2. We can factor the numerator to get the limit of x minus 3 squared times x plus 2 squared divided by x plus 2. What we can do now is cancel x plus 2 in the numerator and denominator, so we get the limit of x minus 3 squared times x plus 2. Here, we can directly substitute negative 2 into the function. So we get the limit of this function as x approaches negative 2 is equal to 0. Now what to do about limits involving radicals? Well, if you have a polynomial under a root, it's quite simple. Remember, a root is just a special case of a power, where the power is a rational number. So using the power limit theorem, additivity limit theorem, and constant multiple limit theorem, we can get the following. Simply distribute the limit under the root sign, and evaluate the polynomial like we would any other polynomial, by direct substitution. Now if you have something more complicated, you might need to multiply by something called the conjugate. So let's give an example. Suppose we want to find the limit of the square root of 4x plus 1 minus 3 divided by x minus 2 as x approaches 2. If we try direct substitution, you'll notice that the denominator will be 0. So the first thing we'll do is multiply the numerator and denominator by the conjugate. So we multiply the numerator and denominator by the square root of 4x plus 1 plus 3. Since we've done that, we can use FOIL and it will get rid of the square root in the numerator. So we get the numerator to be 4x plus 1 minus 9. And we can simplify the numerator and factor and get 4 times x minus 2. We can now see that we can cancel x minus 2 in the numerator and denominator and then directly substitute 2 into the resulting function. So as a result, we get the limit of the function is equal to 2 over 3. Now let's talk about evaluating side limits. Let's evaluate the limit of 2 minus x divided by the absolute value of 2 minus x as x approaches 2 from the right. Now notice, as x approaches 2 from the right, 2 minus x will be negative. So in the denominator where we have the absolute value of 2 minus x, we're really dealing with the negative case. So this simplifies to the limit of 2 minus x divided by negative 2 minus x. We can cancel the 2 minus x in the numerator and denominator and get that the limit is equal to negative 1. Here's another example. We want to evaluate the limit of x squared minus 2 divided by x squared plus 2x minus 3 as x approaches 1 from the left. So let's first begin by rewriting the limit. So what we need to do now is factor the denominator, which will give x plus 3 times x minus 1. We can then apply the product limit theorem and get the limit of x squared minus 2 divided by x plus 3 as x approaches 1 from the left, times the limit of 1 over x minus 1 as x approaches 1 from the left. Now we can solve the first limit simply by direct substitution and get negative 1 over 4. Now as x approaches negative 1 from the left, x minus 1 tends towards a very small negative number. Therefore, 1 over x minus 1 tends towards negative infinity. However, we have negative 1 over 4 in the front, so the whole thing is going to tend towards positive infinity. As an exercise, try to compute this limit as x approaches 1 from the right. Now let's go over a very useful technique called change of variable. Suppose we want to evaluate the limit of 2x divided by x plus 27 raised to the power of 1 over 3 minus 3 as x approaches 0. Notice, if you try direct substitution, you'll get 0 over 0, which is an indeterminate form. So how can we compute this limit? Now notice in the denominator, we have x plus 27 raised to the power of 1 over 3. That seems a little bit tricky to deal with. So how about let's let that whole thing equal u. So u is equal to x plus 27 raised to the power of 1 over 3. Now because u is equal to x plus 27 raised to the power of 1 over 3, x is equal to u to the 3 minus 27. Now what does u approach as x approaches 0? Well, we can just take our expression for u in terms of x and plug in 0. So we get as x approaches 0, u approaches 3. Now we can rewrite the limit. Remember, x is equal to u to the 3 minus 27, and u is equal to x plus 27 to the 1 over 3. So we can simply make our substitution and get 2 times u to the 3 minus 27 divided by u minus 3 as u approaches 3. This is much easier to deal with because u to the 3 minus 27 is the difference of cubes. Now we can use our difference of cubes expansion and get 2 times u minus 3 times u squared minus 3u plus 3 squared, all divided by u minus 3. Notice we can cancel out u minus 3 in the numerator and denominator to get the following. And because this is just a polynomial, we can directly substitute 3 into the function. And finally, we get that the limit is equal to 18. This may seem a little bit tricky at first, so let's go over another example. Let's try to evaluate the limit of tan 3x times cos x squared divided by 4x as x approaches 0. First, notice that tan 3x is equal to sine 3x divided by cosine 3x. So we can rewrite the limit and substitute this new expression for tan x. Once we've done that, we can do a little bit of simplifying and move cos 3x into the denominator. Here, we can just use the product limit theorem. We can do the limit of cos x squared divided by cos 3x as x approaches 0 times the limit of sine 3x divided by 4x as x approaches 0. And notice that the limit of cos x squared divided by cos 3x as x approaches 0 is equal to 1. So we can just focus on the limit sine of 3x divided by 4x as x approaches 0. Now a tricky part is sine of 3x, so let's let u equal 3x. If u is equal to 3x, then x is equal to u over 3. Note that as x approaches 0, u approaches 0 as well. We did this just by substituting 0 into our equation for u in terms of x. So we have the limit of sine of u over 4 times u over 3 as u approaches 0. We can simplify this to get the limit of 3 times sine u divided by 4u as u approaches 0. Again, we can use the product limit theorem and pull 3 over 4 out of the limit. So now we have the limit of sine u over u as u approaches 0. If you recall from the last video, this limit is equal to 1. So we have the whole limit is equal to 3 over 4. And now let's move on to our final example of change of variable. Let's say we want to evaluate the limit of cos x minus 1 divided by x as x approaches 0. What we're going to do first is apply trig identity. Notice that cos x is equal to 1 minus 2 times sine squared of x over 2. We can substitute this expression for cos x into the limit and get the following. Now in the numerator we have 1 minus 1, which is of course 0. So we have the limit of negative 2 times sine squared of x over 2 divided by x as x approaches 0. And of course, applying the product limit theorem, we can take negative 2 out of the limit. So once again, we can identify the tricky part of this limit. The tricky part is the x over 2 in the sine function. So we can let u equal x over 2. If u is equal to x over 2, then x is equal to 2u. And note that as x approaches 0, u also approaches 0. So now we can rewrite the limit in terms of u. We have negative 2 times the limit of sine squared u divided by 2u as u approaches 0. So notice here in the denominator we have 2, and we have a negative 2 coefficient, so we can cancel that to give negative 1. And also notice that sine squared u is equal to sine u times sine u. So we can get negative 1 times the limit of sine u over u times sine u as u approaches 0. And remember, the limit of sine u divided by u as u approaches 0 is equal to 1. So we can apply the product limit theorem and get negative 1 times the limit of sine u over u as u approaches 0 times the limit of sine u as u approaches 0. And this is just equal to negative 1 times 0, which is equal to 0. Now let's talk about limits at infinity. Limits at infinity for polynomial functions are pretty trivial, so I won't cover that here. What I will cover are limits at infinity of rational functions. So suppose we want to evaluate the limit of 3x squared plus 5x minus 2 divided by 2x squared minus x plus 7 as x approaches infinity. To do this, we can divide the numerator and denominator by the highest power of x. So here, that's x squared. So if we divide the numerator and denominator by x squared, it looks like this. And we can cancel out all of the x's. So we get the limit of 3 plus 5 over x minus 2 over x squared divided by 2 minus 1 over x plus 7 over x squared, all as x approaches infinity. We can now apply the useful limit that we proved in our last video. That is, the limit of 1 over x to the n as x approaches infinity is equal to 0. So now note we have the following. We can distribute the limit into the numerator and denominator by the rational function limit theorem and the additivity limit theorem. Evaluating all the limits, we get 3 plus 0 minus 0 divided by 2 minus 0 plus 0, and this is equal to 3 over 2. So the limit of 3x squared plus 5x minus 2 divided by 2x squared minus x plus 7 as x approaches infinity is equal to 3 over 2. Let's do two examples of the squeeze limit theorem. Suppose we want to evaluate the limit of x squared times cos of 1 over x as x approaches 0. Now if you try to directly substitute x is equal to 0, you'll run into a few problems. What you'll notice is you'll have 0 times cos of infinity, which is of course something that we can't calculate. So let's try to apply the squeeze limit theorem to this limit. First notice that cosine of 1 over x is always between negative 1 and 1. This is because cosine is always between negative 1 and 1. So we can multiply x squared throughout the inequality and get negative x squared is less than or equal to x squared times cos of 1 over x, which is less than or equal to x squared. Now note that the limit of negative x squared as x approaches 0 is equal to 0, and the limit of x squared as x approaches 0 is also equal to 0. Therefore, by the squeeze limit theorem, the limit of x squared times cos of 1 over x as x approaches 0 must also equal to 0. Let's try to evaluate the limit of sine of x plus 2x times cos of x divided by x squared as x approaches infinity. Now this would be a pretty difficult function to directly apply the squeeze limit theorem to, so we can split up the function into two separate functions. We have the limit of sine of x divided by x squared as x approaches infinity, plus the limit of 2 times cos of x divided by x as x approaches infinity. So now we can apply the squeeze limit theorem to each limit separately. So first notice that sine of x is always between negative 1 and 1. We can divide x squared throughout the inequality and get negative 1 divided by x squared is less than or equal to sine of x divided by x squared, which is less than or equal to 1 divided by x squared. Now notice that negative 1 divided by x squared as x approaches infinity is equal to 0, and 1 over x squared as x approaches infinity is also equal to 0. So therefore, the limit of sine of x divided by x squared as x approaches infinity must also equal to 0. We can now apply the squeeze limit theorem to our second limit. So remember, cos of x is always between negative 1 and 1. Here, we can multiply by 2 and divide by x throughout the inequality. So we have negative 2 over x is less than or equal to 2 times cos of x divided by x, which is less than or equal to 2 divided by x. Again, we can take the limit of negative 2 over x and 2 over x as x approaches infinity, and we'll get that both the limits are equal to 0. Therefore, the limit of 2 times cos of x divided by x as x approaches infinity is equal to 0. So by the squeeze limit theorem, the limit of sine x plus 2x times cos x divided by x squared as x approaches infinity is equal to 0 plus 0, which is equal to 0. And finally, let's go over an example where the limit does not exist. So let's try to evaluate the limit of 1 over x minus 2 times x minus 6 divided by x squared plus 4 as x approaches 2. First, let's apply the product limit theorem. So we have the limit of 1 over x minus 2 times x minus 6 divided by x squared plus 4 as x approaches 2 is equal to the limit of 1 over x minus 2 as x approaches 2 times the limit of x minus 6 divided by x squared plus 4 as x approaches 2. We can evaluate the second limit easily and get negative 1 over 2. So now we have negative 1 over 2 times the limit of 1 over x minus 2 as x approaches 2. So let's try to analyze the behavior of this function as x approaches 2 from the right and as x approaches 2 from the left. So the limit of 1 over x minus 2 as x approaches 2 from the right is equal to infinity, and as x approaches 2 from the left is equal to negative infinity. So the side limits are not the same. Therefore, the whole limit does not exist. To fully understand how to calculate limits using the limit laws, I highly recommend trying some examples yourself.